Imagine you are standing on the surface of Mars, not in a simulation, not in a photograph. Actually there, the ground beneath your boots is rust-colored and fine, like powdered brick. The sky above you is not black and not blue, but a pale, dusty pink, the color of a sunset that never ends. The temperature outside your suit is somewhere around -60 degrees Celsius. The atmospheric pressure is less than 1% of what you breathe on Earth. You can see the horizon. It is closer than you expect. Mars is smaller than Earth, so the curvature drops away faster, and standing on the surface you feel like you are on top of something rather than inside something. Like you are perched at the edge of the world rather than standing on its floor. You have been here for 8 months. The journey from Earth took that long, traveling at the right moment in the orbital cycle when Earth and Mars are as close as they get. You launched when the window opened, burned hard to leave Earth's gravity, and then coasted for the better part of a year through the silence between worlds. Now you are here, and you are looking up at the sky, and somewhere up there, so small it barely registers as a point of light, is Earth. It takes 11 minutes for a radio signal to reach you from home. You cannot have a real conversation with anyone you love. You ask a question and wait 11 minutes for the answer. They ask how you are and wait 11 minutes to hear. Everything is delayed. Everything is separated by 11 light minutes of cold vacuum and the physics of electromagnetic radiation traveling at the speed of light. You are further from home than any human being has ever been. And here is the thing that nobody talks about enough. The thing that the mission briefings address in technical language and the training simulations cannot fully prepare you for. You cannot leave. Not now. Not when you want to. Not if something goes wrong in a way that requires you to be on Earth immediately. The orbital mechanics that brought you here only work at specific windows, moments when the positions of Earth and Mars align in a way that makes the journey possible with the fuel you have. Those windows open approximately every 26 months. You arrived at one window. The next window is 26 months away. You are staying, whether you want to or not. And that is just Mars. It only gets worse from here. Let's start at the beginning. Not Mars, not even the moon. Let's start with the basic physics of leaving Earth, because it is the foundation of everything that follows, and it is more brutal than most people appreciate. Earth is a planet with significant gravity. To escape that gravity, to reach orbit, to get off the planet entirely, requires reaching a specific velocity. For low Earth orbit, that velocity is approximately 7.9 kilometers per second. For escaping Earth's gravity entirely and heading into deep space, it is approximately 11.2 kilometers per second. 11.2 kilometers per second. Every second, you are moving 11 kilometers. That is roughly 40,000 kilometers per hour. That is the minimum speed required to leave Earth and not fall back. Getting to that speed requires an enormous amount of energy, which means an enormous amount of fuel. And here is the brutal reality of rocket engineering. Fuel has mass. Mass requires more fuel to accelerate. More fuel means more mass. More mass means you need even more fuel. The relationship between the mass of fuel required and the velocity you want to achieve is not linear, it is exponential. This relationship, described by the Tsiolkovsky rocket equation, means that getting anywhere significant requires carrying truly staggering amounts of propellant. The Saturn V rocket that carried Apollo astronauts to the moon stood 111 meters tall and weighed approximately 2.8 million kilograms at launch. Of that mass, the actual payload that reached the moon and returned was a few thousand kilograms. The capsule, the crew, their equipment, everything else was fuel that was burned to get them there and then thrown away. This is the fundamental challenge of space travel. Not the destination, not the conditions at the destination, getting off the ground in the first place. Every destination we discuss in this video begins with this challenge. And every destination adds its own layer of impossibility on top of it. The moon is the closest thing humanity has ever reached beyond Earth. It sits approximately 384,000 kilometers away. The Apollo missions covered that distance in roughly 3 days. A relatively manageable timeline, a relatively manageable distance. If something goes wrong on the moon, you can be home in 3 days. And yet, getting humans to the moon and back was one of the most technically demanding achievements in human history. It required a decade of development, the largest rocket ever built, the most sophisticated engineering of its era, and it succeeded with margins so thin that it is, in retrospect, astonishing that all 6 successful landings went as planned. The Apollo 13 mission, launched in April 1970, did not go as planned. An oxygen tank in the service module exploded 2 days after launch, crippling the spacecraft. 3 astronauts, Jim Lovell, Jack Swigert, and Fred Hayes, had to abandon the main spacecraft and shelter in the lunar module, a small craft designed for a brief stay near the moon's surface rather than 4 days of emergency survival in space. They made it back through an extraordinary combination of engineering improvisation, mission control expertise, and the fact that the laws of orbital mechanics still provided a path home even after the crisis. 3 days from Earth, and it came this close to killing everyone aboard. Now think about what happens as the distance grows. The moon has problems of its own that often go undiscussed in the excitement about returning there. The surface of the moon has no magnetic field protecting it from the solar wind, the constant stream of charged particles flowing outward from the sun. Earth's magnetic field deflects most of this radiation. The moon has no such protection. Standing on the lunar surface, you are exposed to a continuous bombardment of radiation that would accumulate over time to dangerous levels. For a short stay, a few days as the Apollo astronauts experienced, the radiation dose is manageable. For a long-term settlement, the radiation becomes a serious problem. The solution is to build underground. Under several meters of lunar regolith, the radiation exposure drops to acceptable levels. But you cannot simply dig a habitat into the moon. The engineering required is substantial, the timeline is long, and until it is done, the people on the surface are accumulating damage in their cells at rates that increase their lifetime cancer risk with every hour of exposure. Then there is the dust. Lunar regolith is not like sand or soil. It has never been weathered. No wind, no water, no organic processes have ever rounded its edges or broken down its structure. The particles are sharp, jagged, almost crystalline in their microscopic geometry. They cling electrostatically to everything, to suits, to equipment, to surfaces. They are almost impossible to fully remove. Breathed in, they would embed in lung tissue and cause long-term damage. In contact with mechanical systems, they act as an abrasive, grinding away surfaces and mechanisms over time. The Apollo astronauts noticed the dust problem immediately. After moonwalks, their suits were coated in gray powder that transferred to everything they touched inside the lander. The smell, they reported, was distinctive, something like gunpowder, though the exact chemistry is still debated. More than one astronaut described mild respiratory irritation even after short surface excursions. For a long-duration lunar settlement, the dust problem is not a minor inconvenience. It is an engineering challenge that does not have a simple solution. And the moon is only 384,000 kilometers away, a long weekend by cosmic standards. Now let's go further. Let's go to Mars. Mars is, depending on the orbital positions of the 2 planets, between 56 million and 401 million kilometers from Earth. The average distance used for mission planning is approximately 225 million kilometers. At that distance, with current propulsion technology, the journey takes between 6 and 9 months. Most realistic mission architectures plan for approximately 7 to 8 months of transit each way, plus a surface stay of roughly 18 months while waiting for the next launch window back. Total mission duration, approximately 2.5 to 3 years. Think about what 3 years means for the human body in space. In microgravity, the weightless environment of the spacecraft during transit, the human body begins to change. Muscle mass decreases because muscles that are not working against gravity lose their need to maintain strength. bone density decreases because bones that are not bearing weight lose the mechanical stimulus that drives bone maintenance. The cardiovascular system shifts because blood pressure distribution changes when gravity is not pulling blood toward the legs. The vestibular system, the balance mechanism, adapts to a world without a consistent up and down. These changes begin within days of entering microgravity and progress over months. Countermeasures exist. Rigorous exercise regimes using specialized equipment can slow but not fully prevent the losses. After a long-duration spaceflight, returning astronauts typically need weeks to months of rehabilitation to recover their Earth-adapted physiology. Standing upright again is initially difficult. Balance is impaired. The simple act of walking feels unfamiliar. The International Space Station gives us the best data on this. Astronauts returning from 6-month expeditions show measurable bone density loss, muscle atrophy, and cardiovascular deconditioning. Extending missions to 12 months and beyond shows that the rate of some changes slows over time but does not stop. A Mars transit of 7 to 8 months would produce significant physiological deconditioning in every crew member before they have even reached the surface. And then they have to land on Mars. Landing on Mars requires the crew to perform precise, demanding tasks while dealing with bodies that have been floating in weightlessness for 7 months. The entry, descent, and landing sequence for a crewed Mars mission, navigating through the thin Martian atmosphere, deploying parachutes, firing retro-rockets, touching down safely, would be the most demanding aviation task ever performed by humans who are not at their physical best. If it works, they then spend 18 months on the Martian surface, in gravity that is 38% of Earth's. Enough gravity to provide some physiological benefit, but different from what the body evolved in. Then they spend another 7 months in microgravity returning to Earth. The total physiological cost of a Mars mission to the human body has never been tested because no human being has ever done it. The extrapolations from shorter missions suggest it is manageable. But manageable and comfortable are not the same thing. Here is the number that changes everything about Mars. The distance means that a signal traveling at the speed of light takes between 3 and 22 minutes to reach Mars from Earth, depending on where the two planets are in their orbits. On average, about 11 minutes. A real-time conversation is impossible. This seems like a communications inconvenience until you think about what it means in practice. The crew on Mars is not operating with the backup of mission control the way Apollo crews did. They cannot call for advice and get an answer before they need to act. A medical emergency cannot be handled by a doctor on Earth in real time. A technical failure cannot be diagnosed by an expert on Earth who asks follow-up questions and gets immediate answers. The Mars crew is, for practical purposes, alone. Every decision they make has to be made by the people on the surface. The mission architecture must account for this. The crew must have the medical training, the technical expertise, the engineering knowledge, and the psychological resilience to handle any situation that arises without meaningful assistance from Earth. And situations will arise. In any mission of 2.5 to 3 years, with equipment operating in a harsh environment, with human bodies under unusual stress, with the random probability that any system can fail at any time, something unexpected will happen. Something for which the training did not specifically prepare the crew. On the Moon, if something goes wrong, you can attempt to return to Earth within 3 days. On Mars, you cannot. The orbital mechanics are fixed. The launch window is fixed. You wait. This is not a theoretical concern. It is a fundamental constraint of the mission that cannot be engineered away without a propulsion technology we do not currently possess. You leave Earth. You commit to 2.5 years. And if something goes wrong 6 months in, you have at minimum 2 more years to deal with it before you can come home. Let's talk about radiation on the way to Mars, because this is perhaps the most underappreciated problem in human Mars mission planning, and the numbers are genuinely alarming. Between the planets, there is no atmosphere, no magnetic field, and no protection from the radiation that fills interplanetary space. That radiation comes from 2 sources. The first is the sun. Solar energetic particle events, eruptions from the sun's surface that release intense bursts of high-energy particles, can deliver dangerous radiation doses within hours. On Earth, we are protected by the atmosphere and the magnetic field. On the International Space Station in low Earth orbit, we are protected by Earth's magnetic field, which extends around the station. On a spacecraft in interplanetary space, there is no such protection. A major solar energetic particle event during a Mars transit could deliver a lethal dose of radiation to an unprotected crew in a matter of hours. Shielding helps. Heavy materials, water, polyethylene, certain metal alloys, absorb some of the radiation. But complete protection against a major solar particle event would require so much mass that the spacecraft would be impractical to launch. Current mission architectures include a shelter area with enhanced shielding where the crew retreats during solar events, hoping that sufficient shielding combined with the duration of the event leaves the crew below the lethal threshold. Hoping. The second source is galactic cosmic rays, high-energy particles, primarily protons and heavier atomic nuclei, originating outside the solar system from distant supernovae and other extreme events. These particles are so energetic that no practical amount of shielding can stop them. They pass through spacecraft walls, through human tissue, through almost anything. When they interact with biological tissue, they ionize atoms, break chemical bonds, and damage DNA. The dose of galactic cosmic radiation received during a Mars transit, 7 to 8 months each way, plus the surface stay, would, by current estimates, use most or all of a crew member's career radiation limit in a single mission. The long-term cancer risk from this radiation exposure is substantial. Some estimates suggest that a Mars crew member returning from a full mission has roughly a 2 to 3% increased lifetime risk of dying from a radiation-induced cancer. NASA's current permissible exposure limits are set to keep individual cancer risk increases below 3% over a career. A single Mars mission essentially uses that entire budget. This is not a problem with a simple engineering solution. Galactic cosmic rays are a fundamental feature of interplanetary space. They cannot be shielded against without masses of material that cannot be practically launched. They are a permanent, unavoidable cost of traveling to Mars. Every crew member who goes to Mars accepts this cost. Every cell in their body absorbs damage throughout the mission that it cannot fully repair. The cumulative effect over the years that follow the mission is a small but real increase in the probability that they develop a cancer they would not otherwise have developed. This is the price of going. It is not paid on landing. It is paid later, quietly, in the cells that were damaged during the journey. Now let's talk about what you actually do if you want to come back from Mars. The return journey requires launching from the Martian surface. This sounds obvious, but the implications are significant. The spacecraft that carries the crew back to Earth, or at least the ascent vehicle that gets them off the surface and to the transit vehicle waiting in orbit, has to either be carried from Earth during the initial mission or manufactured on Mars or sent ahead unmanned before the crew arrives. If it is carried from Earth, it adds enormous mass to the initial launch, making the mission exponentially more expensive and difficult. If it is manufactured on Mars, it requires industrial capabilities on the Martian surface that do not currently exist and would take years or decades to establish. If it is sent ahead unmanned, it must survive the journey to Mars, land successfully without a crew to intervene if something goes wrong, and then wait for months or years on the Martian surface before the crew arrives. The most realistic current mission architectures use the third option. A return vehicle is sent to Mars ahead of the crew. It lands unmanned. It is powered by a nuclear reactor or solar panels. It begins producing propellant from the Martian atmosphere and soil using a process called in situ resource utilization, essentially making rocket fuel on Mars from available materials. This sounds elegant, and it is in principle. Mars's thin atmosphere is mostly carbon dioxide. Combining carbon dioxide with hydrogen brought from Earth using the Sabatier reaction can produce methane and water. The water can be electrolyzed into hydrogen and oxygen. Methane and oxygen together make rocket propellant. In principle. In practice, this requires a nuclear reactor operating reliably in the Martian environment for years before the crew arrives. It requires chemical processing equipment operating reliably in temperatures that swing from -70 degrees at night to +20 degrees in the afternoon, in an atmosphere with frequent dust storms that can reduce solar power generation to near zero for weeks at a time. If the propellant production system fails, if the reactor has a problem, if a critical component breaks, if a dust storm lasts longer than anticipated and prevents sufficient power generation, the crew arrives at Mars and discovers that their ticket home is not ready. They wait and wait, using the supplies they brought, rationing, hoping the system can be repaired or that production can catch up. And if it cannot be fixed, they do not come home. The dust storms of Mars deserve their own discussion, because they are unlike anything on Earth and they represent a threat to long-duration Mars missions that is often underestimated. Mars experiences regional dust storms regularly, cyclonic systems that can cover areas the size of continents, reducing visibility and solar power generation significantly. These storms typically last days to weeks. But occasionally, Mars experiences global dust storms, events where the entire planet is enveloped in a dust haze so thick that the surface temperature drops, solar power generation falls to a fraction of normal, and virtually every system dependent on sunlight is compromised. In 2018, a global dust storm lasted for 8 months. The Opportunity rover, which had been operating on Mars for 14 years powered by solar panels, was unable to generate sufficient power to operate and was never heard from again. Its batteries drained in the darkness and it died. Opportunity was a robot. It did not need water, food, or breathable air. It just needed power. A human crew during a global dust storm needs all of these things. Water recycling systems need power. Oxygen generation needs power. Heating needs power. Without it, the habitat cools rapidly in temperatures that can reach -100 degrees Celsius at night. Food preparation needs power. Communication needs power. Navigation and monitoring systems need power. A global dust storm lasting 8 months would be a catastrophic challenge for any Mars mission relying primarily on solar power. Nuclear power is the solution, a reactor that generates power independently of sunlight. But reactors have their own reliability requirements, maintenance needs, and failure modes. The 2018 global dust storm was not predicted in advance with the precision that would have allowed a human crew to prepare fully. Mars weather is complex, and our models of it are still incomplete. A crew on Mars cannot necessarily know that a global storm is coming soon enough to take all necessary precautions. This is the environment that people who travel to Mars will live in. Not for a weekend, for 18 months. Here is something that the mission planning documents address in measured technical language, but that deserves to be said plainly. 3 years is a long time for a human mind. The psychological challenges of a Mars mission are as significant as the physical ones, and in some ways more difficult to prepare for. You can train a body, you can build fitness and endurance and resilience, but training the mind for 3 years of confinement, isolation, and the specific psychological pressure of being further from home than any human being has ever been is something that no amount of simulation fully replicates. The crew will be 6 to 8 people, living in a habitat designed to be functional rather than comfortable, in a space roughly equivalent to a large apartment. For 3 years, they will know each other's habits, patterns, irritations, and weaknesses in a way that no ordinary relationship ever achieves. The combination of familiarity and confinement that produces this knowledge can become, over time, either a profound bond or a profound source of tension. Simulations of long-duration confinement missions where volunteers live in isolated habitats for months to test the psychological dynamics have consistently found that interpersonal conflict is one of the primary risks. Not dramatic conflict, subtle conflict, the accumulation of small irritations into resentments, the erosion of patience, the difficulty of maintaining motivation. The asteroid belt begins at approximately 2.2 astronomical units from the Sun and extends to about 3.2 astronomical units. It is not, despite what science fiction often depicts, a dense, dangerous maze of tumbling rocks. The total mass of all the asteroids in the belt is less than 4% of the mass of the Moon, and they are spread across an enormous volume of space. The average distance between significant asteroids is hundreds of thousands of kilometers. But the asteroid belt is still 2 to 3 times farther from Earth than Mars. Communication delays grow from 11 minutes to 20 or 30 minutes. Rescue becomes not merely difficult but essentially impossible. The transit times involved mean that any emergency must be handled entirely by the people on site. Beyond the asteroid belt is Jupiter at 5.2 astronomical units. A signal to Jupiter takes approximately 35 to 45 minutes. A spacecraft traveling at the velocities achievable with current propulsion technology takes years to reach Jupiter. The Galileo probe, launched in 1989, took 6 years to reach Jupiter using gravity assists from Venus and Earth. A human crew could not be sustained for 6 years in transit with current life support technology. The radiation environment around Jupiter is another matter entirely. Jupiter has the most intense magnetic field of any planet in the solar system, and that field traps charged particles in intense radiation belts that would deliver lethal radiation doses in hours or days to any unprotected human. The moons of Jupiter, Europa, Ganymede, Callisto, are embedded in or near these belts. A human mission to the Jovian system would require extraordinary radiation shielding or extremely fast transit that current technology cannot provide. Saturn is at approximately 9.5 astronomical units. A signal takes 80 to 90 minutes. The Cassini spacecraft, launched in 1997, took 7 years to reach Saturn. Uranus is at 19 astronomical units. Neptune is at 30. Pluto ranges from 30 to 50 astronomical units. At Pluto's distance, a signal takes 4 to 8 hours. A round-trip signal, sending a message and receiving a reply, takes 8 to 16 hours. Mission control on Earth effectively cannot provide any meaningful assistance to a crew at that distance. By the time they hear of a problem and send a response, the situation has either resolved itself or killed everyone involved. The outer solar system is not merely far. It is a different category of isolation, a different category of alone, and we have not left the solar system yet. Here is where the numbers stop being comprehensible and start being something else entirely. The nearest star to our own sun is Proxima Centauri, part of the Alpha Centauri system. It sits at a distance of approximately 4.24 light-years. A light-year is the distance that light travels in 1 year. Light travels at 299,792 kilometers per second. In 1 year, it covers approximately 9.46 trillion kilometers. In 4.24 years, it covers approximately 40 trillion kilometers. The distance from Earth to Proxima Centauri is 40 trillion kilometers. Our fastest spacecraft, the Voyager probes, launched in 1977 and now in interstellar space, are traveling at approximately 17 kilometers per second. At that speed, it would take approximately 75,000 years to reach Proxima Centauri. No human mission is possible at Voyager's speed. The people who left Earth would die. Their children would die. Their grandchildren would die. Thousands of generations would be born and die on the spacecraft before it arrived. So let's be generous. Let's imagine a spacecraft that travels at 10% of the speed of light, a velocity that is still far beyond anything current technology can achieve, but within the realm of what physics permits. Such a spacecraft would reach Proxima Centauri in approximately 42 years. 42 years. A person who leaves Earth at 30 years old arrives at Proxima Centauri at 72. If they survive the journey, the radiation, the isolation, the physiological effects of decades in space, they arrive as elderly people who have spent 42 years in a spacecraft. They would look back toward Earth. The signal they send announcing their arrival would take 4.24 years to reach home. The signal they receive in reply would take another 4.24 years to arrive. The people who receive their message of arrival would be more than 8 years older than the people who waved them off. If they wanted to return, if they survived long enough to attempt it, they would arrive back on Earth 84 years after they left. The world they left would be unrecognizable. Everyone they knew would be dead. The civilization that sent them would have changed beyond recognition. They cannot come back. not in any meaningful sense of that word, not to anything they recognize as home. Now add the physics that most discussions of interstellar travel omit. At 10% of the speed of light, the effects of special relativity are small but present. At higher speeds, 20%, 50%, 90%, they become significant. Special relativity tells us that time is not the same for all observers. A clock on a spacecraft moving at high velocity runs slower than a clock on Earth. Not because anything is wrong with the clock, because time itself passes at different rates for observers in relative motion. At 50% of the speed of light, a clock on the spacecraft runs at approximately 87% of the rate of a clock on Earth. A year on the spacecraft is roughly 1.15 years on Earth. At 90% of the speed of light, a clock on the spacecraft runs at approximately 44% of the Earth rate. A year on the spacecraft is roughly 2.3 years on Earth. At 99% of the speed of light, a clock on the spacecraft runs at approximately 14% of the Earth rate. A year on the spacecraft is roughly 7 years on Earth. This sounds like a gift at first. Travel fast enough and you age slowly while the universe ages quickly. A crew traveling at 99% of the speed of light could reach Proxima Centauri in about 4 years of their own experience time, while 4.24 years pass on Earth, barely any difference. But increase the speed further, and you need to go further to more distant stars, and the divergence grows catastrophically. A trip to the center of the galaxy at 99.9% of the speed of light would take about 26 years of the crew's experience time. But 26,000 years would pass on Earth. The crew that left Earth 26,000 years ago returns to find a planet they cannot recognize. Every person they knew has been dead for thousands of years. The civilization that built their spacecraft is gone. The languages they speak may no longer exist. The countries they came from may be geological features now, buried under new cities or returned to nature. Relativistic travel to the stars is not a return journey. It is a one-way trip into an alien future. You do not come back to Earth. Earth moves on without you, at a rate that makes every minute of your journey a year of its history. Let's talk about what it actually takes to reach any meaningful fraction of the speed of light, because the energy requirements are the second wall that interstellar travel runs into after time dilation. The kinetic energy of a moving object increases with the square of its velocity. Double the speed and you need 4 times the energy. Triple the speed and you need 9 times the energy. This relationship, familiar from ordinary physics, becomes even more demanding at relativistic speeds, where the equations of special relativity modify the simple Newtonian formula and make the energy required approach infinity as speed approaches the speed of light. To accelerate a spacecraft with a mass of a few thousand tons, a reasonable estimate for a crewed interstellar mission, to 10% of the speed of light, the energy required is approximately 450 petajoules. A petajoule is 10 to the power of 15 joules. 450 petajoules is roughly equivalent to the total energy output of the United States for about 4 days. To reach 20% of the speed of light, the energy required increases by a factor of 4. To reach 50%, by a factor of 25. To reach 90% by more than a factor of 200. No current energy source can provide this. No foreseeable energy source can provide this at the scale required for a crewed spacecraft. Nuclear fusion, the reaction that powers the sun, could theoretically power an interstellar spacecraft, but the engineering required to harness it for propulsion has not been achieved. Nuclear pulse propulsion, using a series of nuclear explosions to push the spacecraft forward, was studied seriously in the 1950s and 1960s under a program called Project Orion, and the physics works, but the political and environmental barriers to detonating thousands of nuclear weapons in space are significant. The most promising theoretical concept for reaching interstellar speeds without incomprehensible energy requirements is the solar sail pushed by a laser, the breakthrough Starshot concept, proposed in 2016. Tiny lightweight sails, pushed by a powerful Earth-based laser array, could theoretically be accelerated to 20% of the speed of light. The laser required would need to produce about 100 gigawatts of power, 10 times the output of all current solar installations in the United States combined. And the sales would be tiny. Gram scale. There is no conceivable version of this concept that carries a human crew. The physics of reaching another star with human beings aboard requires a solution that does not currently exist, that may not exist for centuries, and that, if it exists at all, will require energy resources and engineering capabilities that current civilization cannot imagine building. You want to travel to the nearest star. The nearest star is 4.24 light-years away. We have no way to get there. Here is the question that follows from everything said so far, and it is the question that turns everything on its head. Why are we so sure that staying is better? Not in the practical sense. Not in the sense that staying is easier, which it clearly is, but in the deeper sense. The sense that matters when you think about what the universe actually is and what humanity's place in it might eventually be. Every civilization that has ever existed on this planet has expanded. Every civilization that has encountered a frontier has eventually crossed it. The reasons are many: resources, curiosity, conflict, the sheer biological drive to move, to explore, to extend the range of what is possible. The stars represent the ultimate frontier. Not a frontier that can be crossed next year or next century, or perhaps even next millennium, but a frontier that exists, that contains destinations, that harbors other worlds around other suns, some of which, statistically almost certainly, have conditions not wholly unlike the conditions that produced us. The distances are real. The energy requirements are real. The physiological costs are real. The psychological demands are real. The impossibility of returning to the world you left is real. All of these things are true, and they are also the same things that were said in different forms about every previous frontier that seemed impassable. The ocean was too wide. The continent was too vast. The mountain range was too high. The desert was too dry. The environment on the other side was too hostile. Every one of these barriers was eventually crossed. Not because the barriers were not real. They were real. People died crossing them. But because the people who crossed them decided that the cost was acceptable and the other side was worth reaching. The stars may be crossed. Not by us. Not by our children. Perhaps not by our civilization as it currently exists, but by something that descends from us, that carries in some form what we built and thought and valued. That crossing will be one way. The people who make it will not come back to the world they left. But neither did the people who crossed the ocean in any meaningful sense. They arrived somewhere new. They made it their world. They built something that did not exist before. The inability to return is not a reason not to go. It is the nature of what it means to truly leave. Let's come back to closer things, to Mars, to the moon, to the human beings who will, in the not-so-distant future, actually go to these places and live with the consequences. Because there are people alive right now who will travel to Mars. Not metaphorically, literally. Human beings who have already been selected, or will be selected in the next decade, who will spend years training and then years in space traveling to and living on another planet. Some of them will not come back. This is not a prediction of disaster. It is the statistical reality of dangerous endeavors. Every significant expansion of human presence into new environments has involved loss. The first explorers to cross oceans did not all return. The first people to climb extreme altitudes did not all survive. The first test pilots to push beyond the sound barrier did not all come home. Mars exploration will involve loss. The only question is whether the cost is accepted as part of the enterprise, the way the cost of oceanic exploration was accepted as part of discovering the Americas, the way the cost of Everest expeditions is accepted as part of climbing the world's highest mountain. If it is accepted, and history suggests that it will be eventually, because the question of whether to go has effectively already been decided by the weight of human curiosity and competitive drive, then the Mars crews who do not return will be remembered in the way that earlier explorers who did not return are remembered, as the ones who went first, the ones who paid the price that made the second mission and the third safer. This is the calculus that space agencies do not say plainly in press releases, but that everyone involved understands. The first Mars mission accepts risks that later missions will not face, because the first mission creates the knowledge that allows later missions to be planned more safely. The people who go know this, and they go anyway. That perhaps is the most extraordinary thing about the whole story. Now let's do something the sleeping orbit videos do so well. Let's make this personal. Imagine you are selected. You are one of 6 people chosen for the first human Mars mission. You have trained for years. You know the risks. You have thought about them, worked through them, accepted them. The day of launch arrives. You sit in the spacecraft. The countdown proceeds. The engines ignite. You feel the acceleration pushing you into your seat, harder than anything you have felt before, as 2 million kilograms of fuel burns in the first minutes of flight. The sky through the window goes from blue to black. The curve of the Earth appears. You are in orbit, and then you leave orbit. The engine burns again. You feel the acceleration for a few minutes. And when the engine cuts out, the silence is complete, and through the window you can see the Earth growing smaller. You watch it for a long time. You can see the continents. You can see the clouds. You can see the blue of the oceans. Then you cannot see the continents anymore. The Earth is a sphere, blue and white, getting smaller. Then it is a disk like a full moon. Then it is a bright point of light among other bright points of light, indistinguishable to the naked eye from nearby planets. And then it is not distinguishable at all. The place you were born, the place everyone you love exists, the entire world of your experience. It has become a mathematical abstraction, a set of coordinates in the darkness, a signal source for the communication system that connects you to mission control. You are going to Mars. You are not coming back for 2.5 years. And though you do not say it to your crewmates in this moment, that you are not certain you are coming back at all. The feeling that produces is not what the training videos describe. The training videos describe something manageable, something that can be worked through with the right psychological tools and crew support protocols. What you feel watching Earth shrink to a point of light in the black is something older than any training, something that no preparation fully addresses, because no human being has ever felt exactly this before. You are alone in a way that has no precedent, and you are only going to Mars. It gets worse from here. 7 months later, the surface of Mars rises up toward you. The descent is violent. The Martian atmosphere, thin as it is, creates heat as you enter it at high speed. The spacecraft glows. The parachutes deploy. The retro rockets fire. The ground approaches at a speed that seems too fast. And then the thrusters cut out and the landing legs absorb the impact. Silence. You are on Mars. The first thing you notice before you open any cameras, before you look at any instruments, is the silence. Not the silence of space, which is the absence of any medium for sound. The silence of a world with an atmosphere thin enough to muffle everything. The wind outside is audible, a faint whisper, but nothing else. No birds, no traffic, no distant human voices, no ocean, no rain, no thunder. The geological silence of a world that has been quiet for billions of years. You go outside. Your first steps on another planet. The suit encases you completely. You cannot feel the ground through your boots in any normal sense. You cannot smell the air. You cannot feel the temperature. You are inside the suit, looking out at Mars through a visor. The sky is pale pink. The ground is rust red, stretching to the horizon in every direction. The rocks are scattered and small, eroded by wind over millions of years. In the distance, a low hill. You look up. Somewhere up there, barely visible in daylight, is Earth. You have a family on Earth. You have friends. You have a home with familiar smells and sounds. You have memories attached to specific places. A kitchen where you ate breakfast every morning. A street where you learned to ride a bike. A view from a window that you did not appreciate until you could no longer see it. Those things are 11 light minutes away. If something goes wrong right now, if your suit springs a leak, if your oxygen supply fails, if you trip and fall and damage your equipment, help cannot reach you in time. By the time any help could be organized on Earth, process the situation, and transmit instructions back, you would either have solved the problem yourself or not. You are the help. You are the only help that exists. This is what it means to be on Mars. Not the exciting version in the mission briefings. The real version. The isolation is absolute. The responsibility is total. And the next launch window home is more than a year away. Now imagine that the return vehicle is not ready. You knew this was a possibility. You were briefed on it. The propellant production system on Mars was sent 2 years before you arrived. It operated on solar power and nuclear backup. It processed the Martian atmosphere and stored the methane and oxygen you need to get off the surface. But a global dust storm hit Mars 4 months before your arrival. Solar power dropped to near zero. The nuclear backup operated, but at reduced capacity. The dust storm lasted 6 months. The propellant production fell behind. When you landed, you were told, the return vehicle is at 70% of required propellant. We will continue production. We expect to reach full capacity within 2 months. 2 months pass. Production is slower than expected. Small equipment issues, nothing catastrophic, but cumulative. You are at 80%. Another month, 85%. The launch window is now 3 months away. The mission planners on Earth are running calculations. Can you launch at 90%? The margins are tighter, but it might be possible. At 85? Very risky. The calculations say you might make it. The calculations also say there is a probability, not large but real, that you do not have enough propellant to complete the Earth return trajectory. The probability that you do not make it home. You are on Mars. Your crewmates are watching you. You are all looking at the same numbers. The launch window does not wait. It opens in 3 months and closes in 3 weeks. If you do not launch in that window, the next one is 26 months away. And your supplies, food, water recycling capacity, oxygen generation, equipment reliability, were sized for the original mission timeline with some margin, not for an additional 26 months. This is not a hypothetical scenario designed to be dramatic. This is a realistic description of the decision space that a Mars crew could face. The people who plan these missions know this. They have spent years trying to design around it. They have added margins, backup systems, redundancies. They have tried to ensure that the propellant production is reliable enough that this situation does not arise. But reliable enough is not the same as certain. And on Mars, certain is not a word that applies to anything. You launch with 87% of the nominal propellant load. The trajectory calculations say you will make it. The margins are thin but positive. You accelerate away from Mars. The planet shrinks behind you the way Earth shrank behind you 7 months ago. The journey home takes 8 months. You monitor the propellant carefully. Every burn is calculated to the kilogram. You take the most fuel-efficient trajectory available, which adds 3 weeks to the journey. 8 months later, you are approaching Earth. The return burns work. The parachutes open. The capsule descends into the ocean. You made it, but not everyone does. Somewhere in the chain of possible missions, in the second one or the third or the fifth, the margins are not enough. The propellant falls short. The trajectory does not close. The crew does not make it home. And the people who watch from Earth receive the last transmission 11 minutes delayed and know that help is impossible. This is the reality of Mars, not the version in the promotional videos. The version that the people who plan these missions think about at 3 in the morning. Let's go back outward, further, because we promised it gets worse, and it does. Beyond the planets, beyond the Kuiper Belt where Pluto orbits, beyond the scattered disk of icy bodies that extends to hundreds of astronomical units from the Sun, there is a region called the Oort cloud. The Oort cloud is not a disk. It is a sphere, a vast, diffuse spherical shell of icy bodies surrounding the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units. It is where long-period comets originate, flung inward toward the Sun by gravitational perturbations from passing stars, or the galactic tide. No spacecraft has ever reached the Oort cloud. Voyager 1, the most distant human-made object, will take approximately 300 years to reach the inner Oort cloud, and it is already more than 45 years into its journey. The Oort cloud extends to approximately 1 to 2 light-years from the Sun. Proxima Centauri is 4.24 light-years away. The Oort cloud and the Oort cloud of the Alpha Centauri system may actually overlap. The outer shells of the two solar systems may be in contact, their icy bodies intermingling in the vast cold space between them. Between the planets and the nearest star, there is not simply emptiness. There is the extended outer solar system, stretching for light years, populated by billions of icy bodies in slowly drifting orbits, unvisited, unmapped in detail, and unreachable by any human mission within any foreseeable timeframe. The solar system is not a tight cluster of planets with a sharp edge. It is a vast, diffuse structure that fills an enormous volume of space. The planets are a small, dense central cluster. The solar system itself extends to distances that make the planetary distances look trivial. And all of it is still within the solar system. The nearest star is beyond all of it. Let's talk about what interstellar space is actually like. Between the stars, the density of matter drops to almost nothing. Not the near vacuum of interplanetary space within the solar system, where the solar wind provides a constant flow of charged particles and the sun's magnetic field structures the environment. True interstellar space. In interstellar space, the density of hydrogen atoms, the most common element in the universe, is approximately 1 atom per cubic centimeter. 1 atom per cubic centimeter. To put this in perspective, the air you breathe contains approximately 27 billion atoms per cubic centimeter. Interstellar space is, by any practical measure, empty. The distances between atoms are measured in centimeters. The radiation environment is the cosmic microwave background, the afterglow of the Big Bang, now cooled to approximately 2.7 degrees above absolute zero, providing an inescapable thermal minimum below which nothing in the universe can cool. And threading through this near emptiness are the galactic cosmic rays we discussed earlier. At interstellar distances, beyond the protective bubble of the sun's magnetic field, the heliosphere, the galactic cosmic ray flux is higher than within the solar system. A spacecraft and crew in interstellar space face even more intense radiation exposure than a spacecraft within the solar system. The void between the stars is cold, nearly empty, and lethally radioactive. There is nowhere to stop. No gravity well to orbit while you make repairs. No resources to harvest. No signal station to contact for help. No possibility of rescue. A spacecraft in interstellar space is entirely self-sufficient by necessity, not by choice. Carries everything it will ever have. When something breaks, the spare part either exists on the spacecraft or it does not. When someone is sick, the medication either exists in the medical kit or it does not. When the crew needs food, it exists in the stores or it does not. There is no resupply, no repair depot, no evacuation. Interstellar travel, if it ever happens, will involve sending people into an environment where they are completely and permanently alone, with no safety net, no backup, and no way home, for timescales that exceed a human lifetime with current propulsion. This is not a challenge that can be addressed by better training or better equipment alone. It is a fundamental redefinition of what it means to be alive in the universe. And yet, there is something in the human story that keeps reaching. The first fish that crawled out of the ocean onto land, if we can use such a metaphor for a process that took millions of years, faced a world it was not designed for. Its gills did not work in air. Its fins were inadequate for locomotion on land. The environment was hostile in ways that would kill most members of its species. But something in the process of life reaches, expands, tries new environments at the cost of enormous failure rates, and occasionally finds something that works, occasionally makes it. The descendants of that fish, including us, inherited a world that the fish's ancestors could not survive in. We are the descendants of something that crossed an impossible barrier. We may be the ancestors of something that crosses the next one. The cost of Mars will be lives. The cost of the outer solar system will be lives. The cost of interstellar travel, if it ever happens, will be everything that a person brings with them when they leave. Their world, their history, their connections to everyone they have ever known. It will be a one-way journey into something completely new. But then, in a sense, so was every significant moment in the history of life on this planet. The ocean is still there. The fish that never crawled onto land are still there. Some of them are doing just fine. The fish that crossed the barrier, the ones whose descendants became amphibians, reptiles, mammals, and eventually us, those fish never came back to the ocean either. They did not need to. They had arrived somewhere new. Sleep well. For those still listening, in the space between waking and sleep, my biggest goal on this channel is to reach 1,000 subscribers. So if you enjoy falling asleep to my videos, please hit that subscribe button. We continue. The moon is 3 days away. Mars is 8 months. The nearest star is 40 years at speeds we cannot achieve, or 75,000 years at the speeds we can. These numbers feel like arguments against going. Reasons to stay. Evidence that the universe is too large, the distances too vast, the physics too unforgiving. But they are also simply the truth of the place we find ourselves. We live on a planet orbiting a star in a galaxy of 400 billion stars. The universe does not owe us proximity. The distances are not arranged for our convenience. The physics is not adjusted to make travel easy. This is simply what the universe is. And in knowing that, in understanding the actual scale of what we live in, something happens. Not discouragement, not despair, something more like clarity. We are here, on this planet, in this moment, with the specific capabilities and limitations that our biology and our technology give us. And somewhere out there, at distances that require new physics to reach and new bodies to survive, are other worlds, other suns, other possibilities. The not going is comfortable. The going is everything else. Outside, the stars are turning slowly as they always do. The moon is somewhere up there, 3 days away. Mars is somewhere, its position calculable to any decimal place you care to specify, its surface conditions known from decades of robotic exploration, its soil composition analyzed in detail by instruments that were never carried in human hands. Waiting, not for us. The universe does not wait, but the possibility is there, has always been there, will be there after everyone now alive is gone. For anyone who comes after who finds a way. The distances are real. So is the reaching. Sleep well.